Today we will just have a look on what are the practical and analysis background for PT in high-rise buildings. Brief overview about what we are going to discuss. We will go through on the basic design assumption and analysis, and what is the actual available effective pre-stress which is considered in design and what could be available at practically at site, and introduction of new openings in existing PT floors. And we will go through the construction sequence which is normally adopted in PT buildings and general and special applications of PT in high-rise buildings. So to start with, a pre-stressing term, it is nothing but we are just trying to introduce some amount of pre-compression before the structure is getting loaded externally. So first we are giving a compressive force which will take all the service load at a later stage based on the amount of service loads. So this can be done by using wire, strand or bar which is introduced into the concrete element. And it can be broadly classified as pre-tensioning and post-tensioning. And pre-tensioning will be done prior to concrete casting in the member. So it will be forces will be held by the anchors, end anchor supports, end blocks, and these will be anchored back through piles. This will be normally done in precast yards. And this type of application will be normally in railway sleepers as well as in buildings where there are identical floor levels at each levels. When the members are going to be identically used, pre-tensioning can be used. And generally in buildings, we use post-tensioning where pre-stressing is applied after the concrete is casted. Here the forces are held temporarily using anchor blocks and wedges. So basic components, stressing end and dead end. The dead end will be anchored into the concrete with sufficient mechanical anchorages to hold the force which is applied through the live end. Then we have vents for grouting after stressing operation is completed, and the ducts will be protecting the strands from ingress of concrete before prior to stressing operation. For slabs, normally up to 300 to 350 mm slab thickness, we use a slab duct, which will be normally used for regular high-rise buildings, and beams for girders as well as for special applications, we use the duct with higher strand capacities. A normal strand will be encased with cementitious grout with a duct strip, which will be corrugated to have better bond, and there will be 7-wire strand. Each and every strand will be 7-wire, and this is the general configuration of component inside the duct. So let us go on to the basic assumption on the analysis and design before we move further. Choosing a proper member size is a major task when we are assuming a PT slab for a flow system. So this size has to meet the primary requirements of ultimate as well as serviceability. So serviceability will be subclassification will be with deflection check and crack width, and ultimate will be with structural strength as well as flexure and shear and torsion. Most basic influencing criteria will be concrete strength, loading, span, and in some cases vibration also forms an influencing criteria. There are various recommendations given by different codes and special editions on the member size. However, whatever member size which we choose, we have to do a detailed check for both serviceability and the strength checks. These can be used as a guidelines to arrive at the initial sizes. Whenever we talk about pre-stressing, we use a concept called load balancing to better understand how it is much different from the regular RCC members. So in post-tensioning, because of profiling of tendons, almost similar to the bending moment diagram, it tries to generate a system of loads. This counteracts the dead load which is expected on the structure. And generally this load balancing is represented as a percentage of dead load, which is balanced. We normally balance for high-rise building to the tune of 60 to 80% of dead load. The reason behind the more dead load which we try to balance, we get a reverse curvature and the finishes might get affected. So that is a practical consideration while taking into account of the load balancing for regular office or residential buildings. Generally, these tendon profiles are reverse parabolas which will exert both upward as well as downward forces in the same span. In an ideal two span with a cantilever, this is a tendon profile which we can expect for a normal slab. So these drapes eventually will try to create an upward load, because once it is trying to straighten up, once we apply a pre-stressing force, it will try to straighten up. So this will create a upward force in the middle of the span and it will dump the load towards the supports. A refined one at the support, we don't want to have a very concentrated load. So we try to take a smooth curvature with points of contraflexure and points of inflection to get a dumping of loads little uniform. So this particular downward load is balanced by a portion of PT with this upward load which is generated due to these profiles. Analytical methods. We adopt generally three methods to analyze post-tension flow system. So simple frame, equivalent frame, and finite element analysis. Simple frame method normally we do for a very rough checking. Here the slabs are designed into separate design strips along the column lines. The geometry of structure is exactly modeled. That is, the stiffness of beams, slabs, and connecting frame are taken exactly. So this doesn't account for any biaxial plate bending. This equivalent frame method is a little refinement from the simple frame method. We use a relative column and beam stiffness. So this accounts for biaxial plate bending. In a typical residential or commercial, when the columns are supported evenly without much variation, this equivalent frame methods give a approximate as well as a safe solution. Normally the degree of approximation depends on the how much deviation from the uniformity and stiffness variation along the span. So in both this method, the design strip from the floor has to be reconstructed, because we don't get a very uniform orthogonal design strips. So we may have to reconstruct that particular design strip to arrive at an approximated frame model. And each and every design strip will be independent, which will be isolated from the adjacent design strips on either side. So basically a design prototype design strip along the column line, we have to reconstruct it with the adjusting the span as well as the bay widths accordingly, so that the final idealized design strip will look something like this. Further moving to the finite element method, we choose this method when there is irregularity in the building, when the stiffness is varying, and when we are not able to predict on the behavior of the structure. This is basically dividing the structure into finite elements, small pieces, so that we capture the localized behavior. And this takes into account of the biaxial behavior of the flow system. So a typical plan of a floor slab which has an irregular layout, we idealize the column support lines on both the directions, both X and Y directions, and then we identify the tributary design strips and we construct design strips for finite element analysis. Here, this finite element analysis, we will have interaction between the adjoining strips, which is not available in the equivalent frame analysis. Then creating of a mesh using fine meshes, and these are the typical load transfer diagram, load flow onto the column. Some of the basic checks for the PT members which we have to do in comparison to RCC. The first check, which will be the serviceability on the stresses. Stresses is a good criteria to decide whether we have chosen the correct size and the correct pre-stressing force, because this depends on these two components, effective pre-stressing force and the cross-section area. The more pre-stressing force if we just try to keep on increasing the pre-stressing force, the stress limits, once it gives an indication that our pre-stressing force is much larger. So a balanced section can be chosen by using the stress limits, which is set by codes as well as the practical limitations. So this moment which is used is the unbalanced moment, out of balance moment, including the pre-stressing effects. So this includes all the effects of applied moment as well as the secondary and pre-stressing primary moment. This basically depends on the grade of concrete. So in case if we have a higher stress levels, then we may have to increase the concrete grade in order to get a better stress limits in the transfer as well as service levels. The other component for this one is the flexural capacity. In addition to the normal flexural capacity given by the untensioned reinforcement, this PT capacity give a higher resistance because of its higher grade. So this also, the formula for this is similar to force into the lever arm, the same method how we approach on the RCC. And initially we check on the elastic deflection. There's nothing but the net deflection from the downward load and the upward load created by the pre-tension, post-tension cables. So the net deflection for the elastic deflection is arrived using this particular method. After this, we need to include the cracking moment, check the cracking moment and see if there is a cracking, then crack deflection as well as long-term creep shrinkage has to be added to this initial elastic deflection. Now, while we are designing the pre-stressed floor, we assume some effective pre-stress after all losses in our analysis. But while in practice, we come across the high-rise buildings with lot of podiums with multiple levels. So basically it is interconnected with huge columns and huge podiums forms a basic part of a PT flow system in a high-rise building. So these stiff columns and stiff core walls will definitely create a kind of a restraint to our PT members. And when we are not able to get the ideal post-strip locations, we need to be careful while we are addressing this particular stiff core walls and columns. In an unrestrained state, when the member can move freely, a compression is effectively transferred and we get an effective pre-stress for that particular system. But once there is a restraint, there is a huge amount of force which will be held back by this particular support, stiff support, which will allow or restrict the movement, and then it will lead to cracks into the system. When a concrete compresses or contracts, or if there's a volume change, it introduces compression to the reinforcement, which is a part of concrete. So this compression on reinforcement in turn introduces tensile stresses to the surrounding concrete around this reinforcement, which results in cracks. So this restraints, it doesn't only happen because of compression due to PT shortening, it also the volume changes happens due to shrinkage, differential temperature change, creep and PT shortening. So shrinkage is nothing but a volume change of concrete at different stages. In the initial stages, it will be major. So 40 to 60% occurs within 90 days. This shrinkage forms a major component onto the overall contraction or expansion in the concrete element. So the initial shrinkage is around 60 to 70% in the initial period, and then it keeps on moving linearly. This differential temperature change is a factor of length and width of the building without any permanent separation, which normally happens in the podiums, and it depends on the overall member depth. This temperature change normally varies between 10 to 15 to 20% of the overall expansion. Creep. This deformation of member under sustained load causes creep. Even when we are applying pre-compression force, that keeps on shortening over a period of time throughout the life of the structure. So this also adds to certain amount of expansion of the concrete element. Finally, our PT shortening, this applying of pre-compression, this ranges between 5 to 10% of the overall contraction. So in short, we can say that out of the overall 100% volumetric changes, shrinkage component is around 65%, creep is around 10%, elastic shortening 10%, and temperature is around 15%. This is around approximate range normally which happens in a particular floor level. So let us get introduced on the function of a particular post strip. This post strip, normally we try to locate it at 1/3 of the span or 1/4 of the span where there is a lesser moment or lesser stresses in that particular level. It is of 1000 to 1500 mm wide so that we can make proper lapping of reinforcement. This allows the slab to shorten while applying PT force. So one end is free, it moves, it transfers the force, and it also gives allowance for stressing provision. So this is a typical post strip arrangement with anchor blocks on both sides. We are lapping tendon. No rebars has to go continuous within the post strip. Else there will be a restraint in the bar. Here we are just lapping a continuous. It is a lapping. Proper lapping will give a continuous bar. So movement happens on both the sides, and then there will be free movement before concreting this particular post strip on both sides. After concreting, the rebar, due to long-term effects like creep and shrinkage, there is no effect of restraint onto the bars which is attached to one end of post strip. After a prescribed period of time, normally around 2 to 3 weeks, the post strip is casted back so that we get a continuous flow. There is no cantilevering effect. So this duration normally accounts for elastic shortening, initial elastic shortening due to PT, and certain amount of shrinkage, initial shrinkage which occurs while the post strip is open. While PT shortening is happening, the column will not get adequate axial force as expected to the as-built condition. If it is a 50-story building, when we are at the first story or second story, the vertical members will not achieve that much of axial compression while we are constructing that particular floor level. When this temperature and shrinkage as a whole tries to address this, but tries to come into action, at that time the axial force onto the column will create enough restraint and it will not allow the slab to move freely. So this shrinkage and temperature movement restraint still exist even if the post strip is filled after 2 to 3 weeks after stressing. So once post strip is casted, the restraint which is cast due to the connection to the other elements, once post strip is casted, then adjoining slab is also gets connected. So that will also create a restraint. So out of the overall restraints, 10 to 20% can be addressed using this post strip. In addition to this, there are some end restraints which happens when there is a fresh concrete laid on top of a existing floor. It happens when we are casting as 2 stages of casting for transfer plate, when there is a suspended slab which is casted over a rigid core wall or rigid column, and when the basement or gown slab is casted exactly on the piles. So this results in lesser than expected pre-stress in slab. So this reduced P/A will not affect the load balancing, and in turn deflection will be intact because of the load balancing basically depends on tendon force as well as drape. And ultimate strength will also not be affected because we have enough concrete and rebar capacity in that particular area. However, reduced P/A will result in more cracking, and this will result in more long-term deflection. One structure cracks, then we get long-term deformations onto the system. Generally, pre-stressed tendons provide a good crack control till the concrete cracks. So once a concrete cracks, the tendons are spaced apart, so it may not be so helpful to control that particular cracks. PT slabs will be subjected to more restrained cracks because we provide nominal untensioned reinforcement in slabs. So at the critical portions, identified portion, top and bottom reinforcement will be able to address these cracks in a much better way. For lower levels where there are higher restraints, additional reinforcement will be helpful in this particular location with a closer spacing. And this restraint is will also impact the weak column. In case of weak column or a wall with a very huge beam, with a strong beam and a weak column junction, when there is a compression happening, then the supports will tend to crack. So having a slender support and introducing higher PORA will be detrimental to the structure. Inversely, when we have a rigid support, then we have to try to use pre-stress at a balanced portion. Otherwise, that will also create restraint cracks because these stiff supports will not allow to shorten. So restraints in slabs results in a lesser than expected PORA if not addressed properly. And higher PORA will be detrimental in a weak column as well as stiff column conditions. Next, we will move on to when we have a post-tension slab which has been constructed, introducing new opening onto the PT slab. So generally, the spacing between tendons is around 1 meter or minimum 500 mm apart. So introducing any opening in between will not be an issue after construction. So as the tendon spacing is higher, anything in between the tendon, we can check back on the design apart from the column area. This particular area should not be in the critical location. So apart from the column drop area, other portion, if it is within the tendon spacing, it can be easily introduced after checking back with the design. However, bigger openings in case of lift or in case of any escalator openings, it has to be approached similar to RCC. We have to introduce the frames, supporting frames, and then we have to do the openings after checking whether the strands are properly grouted. So the intended opening, and we have to hack and expose the tendon and see how good the grouting is there. Then after that, we have to make a dead ends to get a proper anchorage. So this is a step-by-step procedure to introduce a new opening. We have to support the slab thoroughly, and we have to introduce a new framing beam which has to support the overhangs. Then we need to trim off the strands and create bulb ends so that there is proper anchorage for the after the slabs are cut. Then we have to go ahead with the hacking of the new opening. So when we hack, we have to make sure that we are not disturbing the reinforcement or tendon in position. And then once the hacking is over, we have to rip open the duct surrounding it and see the grout efficiency. Then we have to introduce either dead ends or we have to introduce dummy live anchorages with wedges to hold the forces. Construction sequence. A typical construction sequence for a regular post-tension slabs. First, actually, upon completion of bottom shuttering, nominal reinforcement we'll start laying on the nominal reinforcement. Then upon completion of nominal reinforcement, tendon, bar chas and ducts will be placed initially, and this ducts will be connected to end anchorages with the grout vents. We have to fix the anchorages, end anchorages, so that it is in position while concreting. Cutting off strands, then pushing the strands inside the ducts. Placement of chap bars to create the profiles to get our expected uniform upward loads. Stressing end has to be fixed with bursting and spalling links to withstand the force. Dead end is prepared with grout vents for grouting. Upon completion of tendon laying, So these are strands, block out, casting, galvanized corrugated duct, grout house, and grout vent. So this is a completed with bottom mat and this thing. After that, top mat will be done, and for beams it will be completed. After completion, starting of concreting in progress, we have to make sure there is no tampering of the ducts while concreting. Recess formers has to be removed, and then wedge plate as well as wedges has to be inserted. Stressing operation starts. So we have to measure this elongation and compare this with the theoretical elongation. After completion of stressing, cutting of strands, excess strands, and then starting of patching of stressing pockets, and grout mix, and grout will be pumped from one side, and for consistency, after consistency, the grout will be locked. So these are the general typical construction progress for any high-rise building. In high-rise building, we choose 3 to 4 standard floor systems. One is two-way beam slab and banded beam and slabs and flat slabs. So two-way beams will be used when the loading is too high as well as vibration is needs to be under control. We try to choose that option. Otherwise, PT flat slab provides much flexibility for services. And this waffle slab, we choose at specific requirement where we need to reduce the dead load as well as height, and where we need to we can scoop out the concrete, excess concrete in the portion where it is not required. It needs a specialized mold. This mold can be used repetitively, and this can be used for typical floor buildings. And one-way beam and slab. So some of our standard approach for typical floor systems, regular flat slab for office buildings. The design strips are made in both the directions. And then tendon actions are also accounted, including all the effects. The global behavior is understood. And we take the elastic as well as a crack deflection for the moment contours and the deflection contours. And PT will be more helpful in case of long overhangs. Example, in a 12-meter long overhang with a central opening, the supports are only at all around the corner. This is connecting both the floors. So the girder overhang is analyzed for the stresses and the deformations, and the tendons are provided, straight cables are used. And a brief introduction onto raft slab. Normally PT in raft slab is not so conducive. However, at certain projects, when there is a requirement, this option has been looked out. The subgrade friction and restraining action is a major factor which keeps us away from using pre-stressing in raft slab. As I stated earlier, there will be lot of huge restraint. Here, the restraint will be because of two layers. One is the soil as well as our concrete section, soil, PCC, and our section. So it will not allow a proper transfer of pre-stressing force. And when we reduce the subgrade friction values, lateral load strength as well as strength consideration reduces. So how to balance this? So in order to lower the subgrade friction, it will we are introducing some kind of 3 levels of we create a compacted subgrade with a thin layer of concrete, and then we use a 25 to 50 mm thick sand, and we introduce polyethylene sheets. Basically, this will allow the raft slab to compress initially, and later on shear connector provision will be given to improve the subgrade friction between the wrap slab and the soil below. So this predetermined drilling will help us to improve the subgrade friction effectively at a later stage after the initial prestressing forces applied. So in order to here actually, as it is a kind of a load which is going to come up at a later stage, we are going to stress the structure in stages. So to facilitate this, either we have to provide stressing paints, or if there is going to be filling above this wrap slab, we can use blocks, stressing blocks. We can use stressing paints to stress alternatively, or we can have, when there is a filling, we can have a tapered section, so we can try to do stressing at different stages. In practical purposes, the POA is limited to 0.7 to 1.5 because of lot of restraints which is expected, and reinforcement will be in the range of 0.1 to 0.12% to improve cracking behavior. The advantage basically is it improves on the cracking and deflection behavior, and also in turn it will increase the stiffness. We can handle the minimum amount of non-prestressed steel content is used because of replacement of this Fe grade, lower grade with a higher tension steel. The analysis approaches, we extract the loads from the global analysis, and then individual strips are analyzed with the interaction with the adjoining strips. So the profiles will be inverted. Okay, one more application in case of long spans are Varendel girders. Normally Varendel girders are steel trusses in general which are used in buildings, but in specific cases when its span is around 40 to 50 meters, we use concrete Varendel girders to connect two floors, and this is utilized for high-rise buildings. These are deep trusses, particularly which are efficient for long span. Sometimes it is designed to be full story deep. The top card will be connected to the top floor and lower floor will be connected to the bottom card. Diagonal trusses are always not preferable, so we will try to omit it. So functionally we can pass some services in between the diagonals. This will have finally a rectangular configuration, and this avoids potential because of when we are avoiding the intrusion of diagonal members. This case, there will be also bending as well as shear force in addition to direct tension and compression in a verticals as well as horizontal members. The joints will be heavy, but absence of diagonal will be make it more user friendly in buildings. We can commonly see this in walkways. So in a building, actually, when there was a idea to introduce a transfer girder from lower floor to upper floor level, it was separated into 3 sets of Varendel with 3 box Varendels, so that we achieve the necessary floor height and function without compromising on the overall height of the structure. So the analysis approaches with the rigid joints, all the connecting trusses are made with the rigid joints, and all forces including moment, shear and torsion and axial force interaction is considered in this analysis. One of the advantage of Varendel is it is quite easy because there is point of counterflexure along all ends, so we can do a simplified analysis using Varendel girders. So this pre-compression is utilized to counter the axial tension basically on the lower card. So this is the analysis with RCC as well as PT. Because of huge tension force at the bottom, introduction of PT neutralizes that particular at the bottom card. Transfer plate. In high-rise buildings, when there is a hotel or extensive car parking, we need to pick up some columns at a elevated level. So this transfer plates or transfer girders are used in such scenarios. So here the loads are picked up in this particular floor level with a uniform thickness throughout. So strips, closer strips are analyzed and moments and shears are arrived based on the tendon layout is. These are stress and moment contours. Yeah, similar kind of contours. So girder is used when we need to pick up only a particular location, column at a particular location rather than staggered columns. So here, one of the major challenges in case of any transfer girder or plate is it is too thick. So casting it in 2 stages helps to avoid the shuttering requirement below this particular transfer girder to multiple levels. We normally do casting for first stage at a lower level. This will act as a permanent shuttering for the second cast. So that is the end of the presentation. If there is any queries, please let us know. Yeah.
Thank you very much for that very interesting presentation, Engineer Muthukumar. There are a few queries in the chat box and I can read them out to you. The first one relates to, the first one asks, what is the effective span of a beam to go for post-tension over conventional reinforced concrete construction?
Yeah, 6 meter to 7 meter is the basic span beyond which PT will be advantageous. It becomes more flexural. It becomes more dependent on deflection. So in that case, we can choose above 7 meters should be a cutoff line.
Thank you. The next question is from Engineer Nilan Herath. In case of fire, what is the behavior of the tendons?
Yeah, up to 2-hour fire rating, we have given the cover requirement for the post-tension classes. So after 2 hours fire rating, the first rebar will be the first protection layer. Our tendon will not be exposed to the directly to the fire. But on top of slab, again we have top mesh and then we have a tendon below that. So it will be behaving more or less similar to the RCC. In addition to that, duct cover is there as well as the bonded tendons have a grout in between. So which will again provide one layer of protection. So up to 2 hours to 3 hours, it shouldn't be a issue. Beyond that, it behaves similar to RCC. We may have to do retrofitting to strengthen the structure.
Thank you. The next question is from Engineer Nandana Surya. How do the transfer plates with post-tension behave under seismic conditions?
Yeah, as I stated earlier, the amount of pre-compression levels are kept to a nominal level. We don't overstress so that the ductility of the structure is intact. We don't provide a very lesser thickness. We provide a shear requirement. Whatever shear requirement is there, compared to RCC, PT thickness will not be drastically reduced, similar to a normal floor slab, because it is not a flexural member. It's practically a shear member. So the section and adequate nominal rebar will be there. PT will be adding value to it, and it will have a duct. We provide in such a way that the ductility nature or the movement sway is absorbed by the column and transfer plate junction. So it behaves more or less with a partial pre-stressing.
Thank you. The next question is from Engineer Sasiradhan, and it reads, how to handle design concept techniques for two-way post-tension slab design. I believe maybe concept level sizing of two-way for slab.
Okay, so design concept for two-way PT slab design. Okay, if you ask me as a concept level, I will say load balancing is the first approach which we do. We just take the total dead load. We arrive at what is the amount of balancing which we need to do. And from there, actually, we choose the section because we know what is the limit of stresses. So we now have how much balancing has to be done. So how much rate, then we can come back onto the section. So typically for a two-way slab with the drop panel, it ranges between span by depth ranges between 45 to 48. So in a 10-meter span, 250 with a drop panel 500 will be a basic sizing to start with.
Thank you. I hope that answers the question, Engineer Sasiruddin. If you need to make any more clarifications, you can unmute as well. So we can go on to the next question by Engineer Harshana. When designing the columns which support a pre-stressed slab, what are the considerations to be taken in the design?
Yeah, this again comes back to amount of pre-stressing which we apply. The more pre-stressing we apply, definitely column will have an impact. And theoretically speaking, in case of gravity loads, this PT will reduce the net gravity moment, but we should not take that into consideration. So when we are providing a nominal pre-compression, that is with the column should not be too lean. When we apply a nominal pre-compression less than 1.5 in the range of 1.5, then it will not have any adverse effect onto the column as long as the column is stiff enough to carry its own gravity load. So we should not take the advantage of PT which is provided due to this compression. So the column design has to ignore this additional advantage this PT is giving onto the structure, because it is a, as I said earlier, this effective pre-stress is always a matter of concern. So we cannot take that into concern and we cannot reduce the column rebar or column design. So the best way approach is when the pre-stressing is done as a partial pre-stressing, when too much of PT is not applied, then we can very well ignore that. A lot of literature talks in that particular direction only.
Thank you very much. The next question is from Engineer Mahinda Gamage. It reads, what are the limitations of selecting post-tension slabs? Or what needs to be considered to move from RC to post-tension?
Okay, limitations of PT slabs. There are two major limitations. When we have a large drops, for example, if it is more than 100 mm or 75, above 75 mm, it will be very difficult to profile. It becomes uneconomical. With too many drops, we should never go for a PT. And with too many openings and punctures expected, too many punctures expected. As I said earlier, we can have some punctures, but it cannot be done randomly with too many modification expected. Then also PT will be not advantageous. When the member becomes more flexural and dependent on deflection, then obviously this PT will add value to the overall structural behavior, cracking as well. So that is a point where we have to decide it has become more flexural to handle. Long span, flexural and deflection intensity will always be the best thing to start with, move from RCC to PT.
Thank you. The next question reads, if theoretical elongation cannot be achieved, what precautions should be taken to get the required elongation?
There are two ways. Sometimes the theoretical elongation will be much lesser than the actual one which we have got at site. If the deviation is within plus or minus 8%, code allows us to accept it as it is. Basically, this elongation is a measure of what is the force which has been applied. It is a check made by designer to ensure that there has been force transferred. It will not be a direct correlation, because the friction as well as the actual component at site, there will be some variation. So this, if it is within plus or minus 8%, this can be approved. When it goes above, for example, if the elongation is more than 8%, then we may have to see if there has been any slippage of strand. If there is too much of enormous, then there will be a slippage of strand or something. If there is a lesser elongation, then we may have to again release it, detension it, and again we can. There are some method statement which has been given to address both sides of the spectrum. So we don't need to get panic if there is a deviation from the elongation, because elongation is just a measure which is given for the designer to understand whether the forces are effectively transferred at site based on the actual values for a particular pore, because single strand will not cause any kind of issues as a pore. The effective force creates a balance load for the entire panel. So we have to take it as a whole and we have to see if there is a major deviation. Otherwise, this elongation, if it is within plus or minus 8%, and if that range goes up to 10%, 12%, the method stated procedures can be used. That should not be a problem.
Thank you. The next question is from engineer Jatu Sabesan. Since the reinforcement provided in the slab is very minimal, how is the diaphragm action designed to transfer the lateral load to the shear core? Also, how is post-tension blowout will be treated when we do the post-tensioning for the transfer slab in 2 stages, if the blowout happens in the 2nd stage?
Okay, to the first part, when we have a diaphragm action, when we need to do a transfer to the shear core, top and bottom mesh is recommended, because diaphragm action in the sense, if the lateral is going to be very phenomenal, if it is going to be a very nominal one, we can only provide in the areas where there is a connection happening between the shear core and the slab. If it is a very high seismic zone, then top and bottom mesh can be introduced in the flow slab to give a proper diaphragm action. PT blowout for transfers in 2 stages. Okay. If the blowout happens in the 2nd stage, because normally this PT blowout, I understand it's a bursting of anchor block. So when a transfer floor is done, first stage will be casted with some 30% to 40% of the total concrete thickness. When we do the stressing, we just wait till whether there is a blowout or something. And typically we don't get any blowout in terms of transfer plates or girders. That's the first part, because of the huge thickness available. There will not be any blowout because the concrete section is too huge. In case it happens, it will be happening during the first stage of casting, when our anchor block is it is at a critical junction where there is a double layer is happening. In that case also, blowout is chances of blowout is very minimal, and we cannot do, when we are doing 2nd stage, the blowout happens in the 2nd stage. It cannot happen because we will grout it when the first stage is completed. If it's a transfer girder and if you allow for flows above, before we are going above, we will grout the tendon. So blowout cannot happen at a later stage.
Right, thank you. And the final question from the chat box reads from engineer Daminder reads, how do you ensure proper grouting of the post-tension strands?
Okay, as I stated earlier, the grout mix, cementitious grout mix has to be pressure grouted. After, there are certain procedures, we have to remove the air vents from the ducts, and after removing, we may have to blow it with pressure, and it has to consistently flow from the other side of the grout tube. And after that only we have to, so this is the mechanism which is used internationally to ensure proper grouting in post-tension stands. We have to make sure that that's happening at site.
Thank you very much for answering all the questions given. But I think there's one more question that was just submitted, so I think we can answer that. It is from engineer Sajiv Edrisingha, who asks, how do you manage early age shrinkage before tensioning starts? Do you recommend both top and bottom reinforcement measures?
Okay, early shrinkage, which happens before stressing, most of the cases we have observed that once we apply a pre-compression, that gets addressed most of the time, because PT starts at 4th day or 5th day. So early shrinkage cracks most of the time when the curing is perfect and when the shortening is happening after 4 to 5 days, when 25 to 27 Newton per m² is achieved, then the shrinkage cracks gets addressed because of the compression. So we don't recommend for top and bottom reinforcement for addressing this initial early shrinkage. No.
Thank you. There's a further question by engineer Sanjay Vijayawardena. How to address stress reversal in seismic design of post-tension beams?
Yeah, we do ductility detailing. That is whatever the moment capacity which is required at the support top, 50% M by 2 for beams and M by 3 for slabs, and M by 4 has to be provided at the center top. So ductility reinforcement will be provided to address this reversal capacity, and also the shear links confinement will be done close to the column supports, which will enhance the shear strength at the joint, and it will enable first flexural failure in case of reversal of stresses, which gives adequate time so that there is no shear failure into the system. Yeah.
Great. Thank you very much once again, Engineer Muthukumar. I would like to now invite Engineer Manjula Kumara to deliver the vote of thanks for today's event.
Thank you, Dylan. I hope you all can hear me.
Yes, we can.
Now we have come to the last part of this today's presentation. So I would like to thank Mr. Muthukumar for accepting our invitation and delivering this very informative and interesting presentation. And also I would like to thank Mr. Muthukumar for answering all the questions raised by our participants. Thank you, Mr. Muthukumar. And then I would like to thank our sponsors today, Tokyo Cement Group, for their support to make this event a success, and also we hope their continuous support for us. And then I would like to thank our organizing committee for this arranging question times programs, Mr. Nilan and our executive committee members for their fullest support to make this event a success. And then I would like to thank our associate members chapter, including Mr. Dylan, comparing this event, and also their members for their continuous support to make this event success. And then I would like to thank our secretariat staff, Mr. Elian and also Mr. Indika, for supporting for this event. And also I would like to thank all the participants who participate for today's event, allocating their time and participating with this event. So I would like to thank everyone who has supported in many ways to make this event a success. Thank you very much.